approach. Let's talk about incremental operations, because we'll see something kind of interesting in Python. What we want to evolve from all these micro benchmarks is not this one line of code is faster than this line of code, therefore we should always write this line of code except in the cases where we don't, which is not particularly useful or durable or interesting advice. But instead, why is it that these two have different speeds, and what does that tell us about a general approach? Is it the case that one of these is inherently slower than the other and will always be slower than the other because, for example, it's doing more work, it's using a worse algorithm, it is not amenable to optimizations being added later, whatever the case may be? And so let's really narrow ourselves to the smallest operations we can do. Here, we're going to time how long it takes to do just an integer addition. It takes us 30 nanoseconds to do an integer addition. That's actually relatively slow. In fact, that is very slow. One integer addition plus the attendant bytecode to look up both of these values takes us about 30 nanoseconds. If we were to do a floating point addition, we can see instead of 30 nanoseconds, this takes us 38 nanoseconds. So there's a little bit of additional slowness on our floating point operations. Does that give us guidance that we should use floating point operations instead of integer operations? Probably not. If we were to look at, say, a complex number operation, we can see it's slower than both of those. But what this tells us is not use one versus the other. What decides whether we use a complex number, an integer, or a float is the nature of the problem itself. We can't suddenly say, oh, let's not capture the decimal, the digits after the decimal point because that might be moderately faster. Instead, we'd say, is this a continuous value or is this a discrete value? And when we look at this last example, what we should get from it is not avoid complex numbers in Python, but instead, why is this slow? Well, necessarily, integers and floating point operations have hardware support. Complex number operations require software support. There is no built-in complex type that we can use for this operation. And as a consequence, we have to, in software, add the real components separate from the imaginary components. What we can think here is what we're really measuring or seeing is the difference between hardware support and software support, and being aware of cases where we have hardware support or low-level support versus cases where everything must be done in software. That might be a durable guidance in terms of avoid cases where there's hardware support for the operation and you can do that, for example, an integer add or a floating point add in a NumPy ND array, versus these operations at the Python level where there is necessarily only software support. If we take a look at the decimal module in Python, here we know this is backed by a C module called mpdecimal, but it does require considerable software support. We'll see that this advice is relatively durable. It's actually very slow to work with a decimal module compared to working with regular floating point operations, but there may be a good reason why we choose to work with a decimal module. It may not be the case that this is what decides whether or not we use this. What would decide this is, do we need arbitrary decimal arithmetic or arbitrary precision decimal arithmetic? But instead, it might give us a guidance of, okay, why is this slow in the first place? Let me show you a canonical example of something that's slow in Python. Here, we're performing a dot product of two very large vectors. And we're going to perform that dot product by multiplying each vector and sum them up. And you can see it takes 6 milliseconds for us to perform a naive dot product. We typically show this example in contrast to an example that uses NumPy, where we'll probably see about a 50 times speed up on this versus our NumPy code. And so if we were to try the same thing in NumPy, well, we don't have NumPy installed in all of our versions of Python. That was a little bit too much prep work for us to do to get this session going. But we might say, you know what? Doesn't the Python standard library have an array module included in it? Maybe that can give me something kind of within the scope of the NumPy speedup. Let's see if the array module does any better than the Python list. And when we look at the performance results from this, my gut feeling is, and what we see here is 7 milliseconds versus, let's see how many milliseconds, so 6 milliseconds, a slight slowdown, not particularly a good idea. Why is that the case, though, is a much more interesting question. Consider the following. When we talk about NumPy, we always talk about it in terms of the idea of a restricted computation domain. And it may just seem like 3 words that we shout at you that don't really mean anything. It's probably the case that we made up that term, but it is a reasonable way for us to think about how Python code interacts with other code and places where Python code may or may not be faster or slower. Here's the situation. When we talk about a restricted computation domain, we talk about the difference in code that runs in the pure Python domain and the difference in code that runs in another domain, a domain where we have shed all of the things that make Python slow and instead are operating at the C level, the Fortran level, the Rust level, the Zig level, the assembly level, some level below the extreme dynamic level of Python. When we think about the array module, the purpose of the array module is for packing contiguous values together using as little memory as possible. We know that Python objects are boxed. That is to say, even for a value of 0, there's still a lot of overhead for that value in order to capture the pointer to the type object, the reference count, and whatnot. And you've probably even seen some of that when you did things like sys.getSizeOf, and you saw that the size of just the value 0 is much larger than what you'd expect for an 8-byte integer. Here you can see probably about 20 bytes of overhead over a 64-bit integer. All of that is things like the reference count, the pointer to the type, and any other bookkeeping that's necessary. That bookkeeping must exist at the Python level because Python, unlike some other languages, does not have a boxed versus unboxed dichotomy. It only has box types. When we think about the array module in the standard library, what we're thinking about is a C module that gives us the ability to store unboxed values so we can shrink the total amount of space that we need for just storing a value itself, assuming that those values are machine typed and those values are stored contiguously in memory. Every time we interact with that, we have to pull the value out of one domain into the other domain. We have to rebox the value when we pull it out of the array module, just as we'd have to do the same thing with NumPy. We would anticipate that this line of code here is going to constitute real Python objects at the Python level from these unboxed objects stored at the array level, and that's where we're seeing a slowdown here over the same operation performed on the Python list that can just operate on those values itself. Now, I want to talk a little bit about why Python code is slow, because this will give us some guidance in terms of what can we actually do that isn't just micro benchmarking to say, oh, this happens to be faster, let's do that. Uh-oh, we just upgraded our version of Python, and now that's the slower of our choices. I'm going to use a very simple conceit. Here I have a context manager that can time a block of code. It's not a particularly good context manager for timing a block of code, but it can show us some very broad differences in speed. Here, what I'm going to show you is when we work with Python data in Python containers, understand that a Python container is contiguous. A Python list, a Python set, a Python dictionary are contiguous data structures. In fact, I should put a star when we talk about the Python dictionary because after the split table optimization, the Python dictionary should be contiguous. Prior to the split table optimization, then you might have gaps in the Python dictionary. So what we might anticipate to see if we did a performance measurement is iterating over a Python dictionary, the speed of that might have changed from prior to Python 3.6 to Python 3.6. We don't have a build of Python 3.5, so we can't test this right here, but it's something interesting for you to look into. I say that a Python container is contiguous, but I don't say what parts of the information stored within are contiguous. A Python container is a contiguous block of Python references. So this Python list with 100,000 floating point values is 100,000 contiguous Python references. It is going to be, the data portion will be 800,000 bytes in size, where each element is an 8-byte pointer. The actual data, however, will be discontiguous in memory, or may not be guaranteed to be contiguous in memory. If you look at the way this code works, it's going to do a random 100,000 times. It is very likely that the built-in Python allocator is going to allocate these contiguously in memory, just because it's going to ask for a spot of memory for a floating point value, and it's going to get this spot, then it's going to ask for another spot, it's going to get this spot, and then it's going to get this spot, and so forth and so on. So when we perform our dot product on this operation, we should anticipate that it will be slower than if we did the same thing in NumPy. But if we shuffle the values, we may anticipate seeing a slowdown in this code. And the reason we'd anticipate seeing a slowdown in this code is because the values are shuffled now, the references are still contiguous, but the actual data will become discontiguous. And when we're performing an operation, we can no longer do optimistic memory loads to say, oh, load a bunch of these memory items, and oh, the next item has already been loaded into our cache line, the next item has already been loaded into our cache line. And for a large enough structure, we might think that we might end up having to do a lot more memory loads just because all of the values can't fit into cache. So just shuffling this data, you can see here, led to a 3 times slowdown. Now note, the shuffling of the data is not related to the sortedness of this data. For example, if I do x's.sort and y's.sort, and I sort the data, I would anticipate that this will have the exact same effect as shuffling in that, let's remove that, because what I'm looking at here is not whether the data is sorted by its value. What I'm looking at is whether the data is next to each other, the actual data values are next to each other in memory. So any additional manipulation I do on this data will make a difference. What I can think then is that I'm actually kind of in a pickle here, because if I really wanted to do this as fast as possible for a number of different operations, for example, I not only wanted to very quickly perform a dot product here, and I also quickly wanted to find what the insertion point is here. Well, I know that if the data is sorted, I can find an insertion point using the bisect module in the standard library in log n time. But if it's unsorted, I can probably perform an operation that looks at every value because they'll be contiguous in memory. I'd need to figure out some way to generate these values contiguously, and that may be very difficult for me to do without really reaching into the lower levels of Python. What this exercise here shows us is the following. 1, we generally do not have control of memory layout in Python. We can't pick where something goes when we create it. In other programming languages like C++, you can say create this data at this point in memory, but in Python you can't. In fact, this slowness, despite being so significant, is probably something we simply cannot do anything about, because the speed up that we got in this version is only a side effect of our allocator deciding to put the actual values contiguously in memory, which a later allocator or a different memory layout or some other operations that were done in our program might no longer preserve that behavior. And so as a consequence, we may actually have to, as part of our micro benchmarking or timing, really take into account what happens when the data is discontiguous as a consequence of shuffling it or sorting it, because that's the only thing we can rely on ever really existing. And there may be some noise in our example. But what this also tells us is we stand to gain a lot from any structure that gives us the ability to lay out the memory contiguously. And this is why we might reach for a tool like NumPy, or reach for a tool like the array module, or reach for some other restricted computation domain that we put together using Cython or a ST extension module.